All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today's discussion, fundamentals, power factor correction, and it all starts now. All right. Well, welcome back. And it is Tuesday, and this is pre-recorded. I just want you to know that this is pre-recorded because I am currently at this moment, the electrical safety workshop. So, having said that, I wanted to review I think, an important technical topic that probably a lot of people misunderstand. And don't understand basically what those little gray boxes and sometimes big gray boxes are doing for you. So I thought I'd take a fundamentals approach to talking about power factor correction. Now, but first, before I get there, we did have a question. If you tuned in last Tuesday, we had a discussion about copper-clad aluminum. And the reason we got to copper-clad aluminum was because of the previous week, we were talking about terminations. And one of the topics of terminations that we touched on was the materials of the conductors that were landing on the terminals within equipment or on devices. A copper-clad aluminum is one of those. We're all very familiar with copper. We use it every day. Copper-clad aluminum, though, a little bit... I think there's some mystery behind it. At least there was some mystery for me, and that was sort of what I took based upon some of the input and questions that were coming over the line. So we reached out to a Mr. Peter Gracer, who this is his life, copper-clad aluminum, and he demonstrated that during our 1 hour session with him. And I know I learned something last week, and apparently that was a highly watched video on many different platforms. You know, we go live on multiple platforms. And we got a question that came in. And actually, it was a series of questions. And I want to make sure that I cover them. I received an email I sent the questions over to Mr. Gracer. And I asked his opinion on how to address some of the questions. So now, what I will do is I'm going to read to you what this individual, and I just got to see who it was. This is how raw this is. Okay, it's just like being live. I don't record, I don't edit. So that's the way that goes. So this question came in from a Mr. Roy Fitz, past IAEI Central Florida Division President. Thank you for watching IAEI News Live. Thank you for following the channel. Thanks for your subscription, and thanks for your attention and your questions. So there's no better, I still say this, and I've always said this, there's no better compliment to an author, and in this case, a blogger, whatever you want to call this program, than those who watch, digest, and follow up with questions. Okay, so here is I'm going to read what Mr. Mr. Fitz has said, and then I'm going to give you Peter Gracer's comment on it, and then I'll comment on it as well because I'm here. All right. He never said anything about wire nuts. They used every other word, splice, terminal, and the industry can use it. Tom D was complicit with not telling the truth. Woo, baby. It's a shot across the bow. Why did he not speak about wire nuts? Knowing every job uses wire nuts and all wire nuts are not approved for copper-clad aluminum. Wire nuts are all not UL labeled itself. I guess he meant are not all UL labeled themselves. The wire nut bag is labeled. Okay, so he's saying the bag is labeled, not the nut. Has every wire nut on the market been approved for copper-clad aluminum? Okay, so I want to address the first one, that I was not telling the truth. I'm just going to tell you how I roll with regard to the IAEI news channel, especially when we're live. And I know this is a recorded session. When I'm live, especially when I'm live, my questions might not align with your questions. And that is why I need comments. That is why you need to comment. Even on this video, if you have comments, put them down below. We watch those. And then I will follow up just like this. Now, this happened to be an email, which is great. You can email the IAEI as well with any questions or comments. If there's something that I did not cover that you think I should have covered, please bring it up. I want that. I encourage that. And you know what that shows me? That shows me this gentleman watched, he listened, and he hopefully learned something, but he identified an area that we did not cover, which is true. I never even thought about a wire nut personally. And I don't know if that's a trade word or what it is, a wire termination point. I don't know. When I think about terminations, I use that generally. So in my mind, it's anything that we would be a termination would have to be listed appropriately and marked appropriately for use or for restriction of use of certain products under their lugs. So in any case, so this gentleman was saying, hey, what about these other types of termination? So I asked Peter, Mr. Gracer, about it. And he says, thanks for the question. There is overwhelming evidence and standard copper-clad aluminum wire is suitable for use with twist-on splice connectors. So there's the term. So I think wire nut is a trade name. I don't know. And I've heard people say that. You can't say that. You've got to use the generic term. And I know we don't use that in the code. So Peter is giving us the appropriate term. I don't know. I guess it's appropriate because it sounds generic. Copper-clad aluminum wire is suitable for use with twist-on splice connectors designed for copper wire. The evidence is both empirical from copper-clad aluminum's 1/2 century of performance history in the field. All right, it's hard to argue, but anyway, and scientific from performance testing by nationally recognized testing labs. Now, I have when someone says, hey, this is the way we've been doing it for years, I don't know about that. That's a little bit on the edge for me. I mean, it could be very valid. In someone's experience over 20 years, we have not seen an issue. That doesn't mean it's still the right thing to do. But he followed up with performance testing by nationally recognized testing laboratories. That helps me buy into what he's selling here from an idea or concept. So due to this evidence, Copperweld, which is his manufacturer, so his company, conducts his manufacture with a copper, and is permitted in section. Okay, so he's saying, in addition, 110.3 of NFPA 70 identifies its product for use with twist-on splice connectors suitable for use with copper. So he's saying that he, as a manufacturer, has performance tested his product with those solutions, and in his instructions is saying that that product is identified for use with twist-on splice connectors that are suitable for use with copper. So, what he's saying, as I'm reading this, what he's saying is that it's suitable, that because it's still a copper connection, and I believe he brought this forward in his discussion, that the core is aluminum, the outside is still copper, and it's a high grade of copper, and it performs on that termination identically to copper because the outside is copper. So he says, based upon this identification, a specific connector would need to label or mark not for use with copper-clad aluminum to limit its use with copper-clad aluminum. So his perspective is that his product, based upon testing and in his instructions, is basically saying you can use this on any termination or wire or not wiring device, any twist-on splice connectors that are designed for copper wire. That's his position, and I'm telling you what his position is. So I guess as a manufacturer of devices, I don't have a reason to argue with him. I don't make twist-on splice connectors, so I can't speak to that. If there's anybody out there who makes twist-on splice connectors and you have an opinion on this, pile it on. Comments down below. Well, the questions, his email moved on. And he says, certainly not using wire nuts in a house would be expensive. I don't know. I don't know about that. I don't have an opinion of that either way. I don't know the price of a wire nut. So anyway, or a twist-on splice connector. Okay, he says aluminum wire connectors will work, and he puts large dollar signs. Oh, no, not aluminum. It's Alumicon, and he is specifying. I didn't know what the heck Alumicon was. So he's pointing towards a manufacturer. And Mr. Gracer's response is, this brand of connector was designed to remediate aluminum conductors from the 60s, not copper-clad aluminum, which were installed in the 70s. Okay, so he's talking about a specific device, which he says is expensive. But to Mr. Gracer's point, the concern of aluminum wire in residential homes was that wire that was used and created years ago, which is no longer made, which we learned our lesson, that material composition of aluminum has issues with terminations that would cause the glowing connections and all that jazz. And he's saying that those would work. And I'd almost question, let's read Peter's answer. It is recommended by the Consumer Product Safety Commission to remediate aluminum wire, and that's a fact. It is important to note that the CPSC specifically states that copper-clad aluminum does not apply. Okay, so the CPSC specifically stated that copper-clad aluminum does not apply. The Alumicon splicing device effectively deals with aluminum's surface oxide layer to allow current to flow at splice points. And he did talk about that. Remember, we talked about the oxide layer that develops, and he said it was instantly. So apparently these connectors have a way to deal with that oxide layer and provide that lower resistance current flow. As I explained in the podcast, this is a podcast. I take offense to that. It's not a podcast. This is a vlog. Anyway, I got to talk to Mr. Gracer. The process of manufacturing copper-clad aluminum removes the surface oxide altogether and replaces it with highly conductive oxygen-free copper. This makes for a highly conductive surface that reduces heat at splice points. Again, copper-clad aluminum wire is not aluminum wire. Okay, so I think that Mr. Fitz, what is doing is, he's honing in on residential wiring and honing in on the problems that occurred years ago with aluminum. This is not aluminum. to Mr. Gracer's point, and I think if you go back and watch that video, there was one slide in there, which I should have highlighted a little bit more and asked a little bit more questions on, where they showed the wire going into a vacuum. And I believe that vacuum was needed to prevent oxidation occurring while they're putting on that, while they're not putting on, but while that copper is being bonded with the aluminum. So that's what he means by you're getting rid of that layer. Isn't this awesome? I mean, this is what these questions, this is what drives clarity. And we all have to understand you can have questions. You can be adamantly against something or think that whatever. Pose that question, get it out there on the table, and we will walk down through it. All right. Now, he also said, did not see the math on box fill using the wire. And he says, need bigger boxes. And Peter's point was, good point. And he suggested to consult section 314.16 for guidance on specifics box fill given the conductor sizes. So what Peter did say was you're going to have a larger conductor, and that may influence apparently the box size. So we should all now what that session was not about was doing a box fill calculation. So I was not going to get into box fill calculations. I wasn't going to get into actual sizing of the conductor based on load currents either. We didn't even do that. That's a whole nother process, right? You need to consider the 100% plus the 1.25, all that jazz. We didn't do anything like that. We just wanted to understand what is copper clad aluminum, period. And what about those connection points? Because remember, our springboard was the previous discussion, which was on terminations. So the reason we had Mr. Gracer on our, this program was because we wanted clarity for the termination discussion, not box fill discussion, not ampacity calculation discussion, raceway size, etc. So, but that is a very good point, and thank you, Mr. Fitz, for bringing that out. He said, I was told there was only one receptacle, Eaton, rated copper clad aluminum for number 10 wrapping around the screw. Well, here's my first issue with that. There is no 10 amp receptacle. Oh, he says a number 10 wrapped around. I'm sorry. Okay. Whew, I was like, where's he going with that? It's a number 10, not a 10 amp. In my mind, I was thinking 10 amp. All right, so number 10 wrapped around the screw. Mr. Gracer's response, I don't know of any manufacturer that disallows size 10 American wire gauge for use with commercial or industrial grade receptacles, and that would be a fact. I would agree with that. I'm not aware of any manufacturer of receptacles that would not permit that. I know he knows of at least 3 major U.S. manufacturers that permit size 10 American wire gauge for standard residential or spec grade receptacles. 3 manufacturers. I'm trying to think if there's a 4th manufacturer of a receptacle in the U.S. Can't think. I'm not going to say the names, but I'm only thinking of 3. Is there a 4th U.S. manufacturer of a receptacle? I think there's only 3, but I could be wrong. Copperwell, his organization, has performed extensive testing with many U.S. brands of residential receptacles with size number 10 American wire gauge. I can safely say that most manufacturers are researching that point. I would tend to agree that we all have eyes on this, what's going on in the National Electrical Code, and whether or not there is a desire to use a number 10. But we got to remember, we have 15 and 20 amp receptacles. There's no other, we have a 10 amp receptacle. That's why And that's why, now this is just a general copper clad aluminum discussion. This is nothing to do with what was being proposed in the 2023 cycle, which was 10 amp circuits. We specifically prohibited the use of a 10 amp circuit being connected to a receptacle. And the main reason was there are no 10 amp receptacles. And the concern of the code panel was having a 15 amp receptacle or a 20 amp receptacle on a 10 amp circuit. Not that it would not be protected, because you would have to protect the wire at its ampacity and you would have a receptacle higher. I believe the concern of the panel was being able to plug in a larger load and a nuisance trip of the overcurrent device. I don't know that I share that same concern, but that is, I believe, what the majority of those on the panel supported. And remember, anything I say is my opinion, not the opinion of IAEI, not the opinion of NEMA, not the opinion of Eaton or anybody else. This is Tommy D. That's it. What's come up here is out there. It's all me. And we are live. Well, I'm recording this and unscripted. Okay. Fair and balanced. All right. So that is that one. So it's going to be, and his last comment was, it's going to be harder for the inspector. Now, Peter's response to that was, perhaps at first, like anything else that is new. However, I personally take comfort in the fact that copper-clad aluminum conductors, copper weld conductors, perform excellently in laboratory testing against the same rated copper conductors. NFPA 70 and UL safety standards have referenced copper-clad aluminum for a very long time. It also comforts me, meaning Peter, that the inspector community in our nation is exceptionally well-trained and conscientious. Now, okay, so here's I guess my gut reaction from it's going to be harder. And Peter said it. The National Electrical Code has recognized copper-clad aluminum for many years. I mean, it's in the ampacity tables. It says aluminum or copper-clad aluminum. I'm not sure what is harder, and I don't know. I don't know what the take was from our session last week, but I think maybe Mr. Fitz is thinking that something is changing that's going to require copper-clad aluminum, or it's a new product on the market. It's not new. Copper-clad aluminum has been in the code. If you go to 310.16, which was, depending upon the code, it could be 310.15 BA2 or whatever that number was. But the right hand of this has said, and always has said, aluminum or copper-clad aluminum. Let me, I'm gonna go back to the 14 code. I'm gonna go back to the 14 code, the 310. Yeah, this was the 14 code, 310.15 B16. How did I know? And look, aluminum or copper-clad aluminum. So it's not new. I don't know what's going to be difficult for inspectors. I don't know what has been difficult. I don't know if anybody has had issues with copper-clad. If you're having issues with copper-clad aluminum conductors, that makes it harder for the inspector. Please, I'd love to hear it, and maybe that's an opportunity for clarity to be created by maybe tools, and maybe IAEI can bring some to the table. So that was a question that came in. I hope Mr. Roy Fitz, I hope that Peter answered your question, and I hope that I help you feel a little bit more comfortable with the program. So we are here to help you all apply products and apply them safely. All right, so let's talk about power factor correction fundamentals. All right. So I'm going to go through the fundamentals. And power factor correction is not new to the NEC as well. I'm not sharing anything new that would require anything different. I'm just trying to help you understand what copper-clad aluminum, or I can't get that out of my head now, what power factor correction is, and these are fundamentals. So power factor correction, power factor in itself, just power factor, is a measure of the efficient use of power. Now, that's a pretty broad statement, I know. This is what how Merriam-Webster defines it. The ratio of the mean actual power in an alternating current circuit. So that means power factor is going to be an AC thing. In watts to the apparent power measured in volt amperes. So it's watts to VA, being equal to the cosine of the phase difference between the electromotive force and current. Okay, so what that's telling you is power factor is a ratio, okay? It helps you understand that angle in between voltage and current sine waves. And apparent power measured in VA, and watts, which is real power. All right. Now, where in the National Electrical Code, and I know it's not clear yet, and that's okay, because we are going to work our way through power factor correction and what power factor is. So let's talk about where. First, let's talk a little bit about where in the code do we find power factor referenced. 220.12. So there's two references in 220.12, and I'll give you a little bit of background on this one. 220.12 says a unit load of not less than that specified in table 220.12 for non-dwelling units and the floor determined by the use of calculating the minimum lighting load. So this deals with lighting load. Motors rated less than 1/8 horsepower and connected to a lighting circuit shall be considered general lighting load. So they're lumping some small motors into this calculation. The informational note says the unit value of table 220.12 are based on minimum load conditions and 100% power factor. I'm in the 2020 code, just in case. And may not provide sufficient capacity for the installation contemplated. That's a whole program unto itself. So 220.12, and in 220.12, that's A. So 220.12 is telling us about a load calculation, and it's bringing in power factor. So we should understand that power factor is going to have something to do with loads and load currents, the amount of VA in a power distribution system. We should know that, because what are we doing in Article 220? We're calculating volt amperes. Why are we calculating volt amperes? Because we need to size things like transformers, we need to size conductors, we need to size service equipment. That's why. Now, 220.40, what is 220.40? Let's take a look, and I know you have your book open. 220.40, general. The calculated load of a feeder or service shall not be less than the sum of the loads on the branch circuit supplied, as determined by Part 2 of this article, after any applicable demand factors, blah, 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 blah. Informational note. See example D1A through D10 in informative Annex D. See 220.18b for the maximum load in amperes permitted for lighting units operating at less than 100% power factor. So what's 220.18? Drum roll, please. 220.18 is maximum loads, and they're referencing 220.18b, which is inductive and LED lighting loads. Not operating at unity. We always said a An incandescent bulb operates at unity power factor. Why? It's a resistor, and we're going to talk about this. It's a resistor. LED lights are not unity power factor. It says for circuit supplying lighting units that have ballasts. What other kinds of lights that have ballasts? Inductive and LED. What's another good inductive light? Think about it. Fluorescence. Fluorescent lights. Inductive. For circuit supplying lighting units that have ballasts, transformers, auto transformers, or LED drivers, the calculated load shall be based on the total ampere ratings of such units and not on the total watts of the lamps. That is a very important section. And I'll tell you some history. And I earned a title of Mr. VA during the code cycle where we changed the load VA per square foot in 220.12, and I believe that was in the 2020 cycle. We were looking at ASHRAE standards and documents that have limitations on watts per square foot. And my argument at that task group meeting was we don't size equipment based on watts. We size it based on VA. And one of the comments came back that said, Tom, this is lighting load. It's all unity power factor. And I said, no, it's not unity power factor. Why? Because I'm thinking 210.18b tells me that. And in addition, if you go out to lighting manufacturers or LED driver manufacturers, fluorescent manufacturers, they will tell you power factors. And we do have some of those numbers in this session today. We're going to talk about that. And we're going to talk about what that means too. But I want you to understand power factor is an important piece of applying the National Electrical Code correctly and properly sizing conductors, transformers, etc. So 220.40, read through that. Look at 220.18b as well. All right, now let's move to 430. Why would I be running over to 430? Well, 430 deals with motors, right? And for motors, we know what moves a motor. Magnetic fields. I will have a displacement between voltage and current to get that motor to start. I need a difference of angles. I need power factor to get that motor to do its job. So 430.29, let's take a look at 430.29. 430.29, constant voltage, direct current motors, power resistors. It says, conductors connecting the motor controller to separately mounted power accelerating and dynamic braking resistors in the armature circuit shall have an ampacity not less than the value calculated from table 430.29, blah, blah, blah. If an armature shunt resistor is used, the power accelerating resistor conductor ampacity shall be calculated using the total of motor full load current and armature shunt resistor current. And it says armature shunt resistor conductor shall have an ampacity of not less than the calculated table from 4 using rated shunt resistor at current at full load current. And there is nothing in there about power factor. I don't even know why I highlighted it. All right, moving on. Scratch that one off. 665. I'm surprised that I could have swore there was full load amp for. All right, well, okay, let's move on. Generators, 445.11. It's 430.32A1, 430.32. Let's check 430.32. Let's see if I screwed that one up. A is motors more than a 1 horsepower. And I'm going to A1. A1, separate overload device. There is a service factor in there. Applying selections shall be this count where the power. Okay, so there's an informational note. It says where power factor correction capacitors are installed on the load side of the motor overload device, see 460.9. So this tells us that we may see power factor correction used with motors, and it points us to 460.9. If we go to 460 is capacitors. 460.9 is rating or setting of motor overload device. Where a motor installation includes a capacitor connected on the load side of the motor overload device, the rating or setting of the motor overload device shall be based on the improved power factor of the motor circuit. And what we're going to hopefully help you understand is why it says that in 430.9. In fact, what I need to do is mark this because I want to come back to it when we get to the right location. Okay, so I'm going to mark that page. All right. Now we're going to go to 665.27. 665.27. 665.27. 668. 665.27. Marking. Each heating equipment shall be provided with a nameplate giving the manufacturer's name and model identification and the following input data: line, volts, frequency, number of phases, maximum current, full load kilovolt amperes, and full load power factor. You notice it says full load power factor. I'll explain to you why later. Additional data shall be permitted. And 665 is on induction and dielectric heating equipment. All right, so those are just a sampling of, in the National Electrical Code, actual text language. We also have Chapter 9, Table 9. What do we see here? Effective Z at 0.85 power factor. If you don't understand what power factor is, how do you understand what this is and what that's and why it's telling you what it's telling you? So power factor correction capacitors are listed to UL standard 810, which is the standard for capacitors. Now, the reason I'm throwing UL 508A up there is because when you apply power factor correction in a power distribution system, you are going to be thinking about resonance, series resonance. And how do you do that? And what you may do, how do you address any resonance issues, any harmonic concerns? You may add capacitors, but also add a filter. And many manufacturers create these in these big gray boxes that include the filters, or small gray boxes, depending upon how large. And that is an assembly of capacitors, which is a UL 810 product, but because it's an assembly, it will be listed to UL 508A, standard for the construction of industrial control panels. So UL 508A will tell you how to put it all together in the right recipe. Hopefully that makes sense. So power factor is not something you want to get rid of. You need power factor to run. And why? Many inductive loads, like motors, need that difference between voltage and current. So what happens? Think about what you're doing. When you energize a motor, you have got a stator and you have a rotor and a stator. You are putting a voltage across an iron core, a coil, which is creating flux. And that flux that's created, when it's being created before anything moves, is power that is not doing any work, right? It's not doing any work, but it's needed to get that difference, to get that rotor to start turning. So when I energize a stator, I have coils of wire, I have iron, slices of iron that I am creating a flux, magnetization, so to speak. And I am trying to create a field that is rotating. And what happens is my rotor starts to turn with it. And there will be a displacement. I will generate, my voltage will start first before my current starts, because my voltage is creating a field and then my current starts flowing. So I will have a difference between voltage and current sine waves, and that angle degree difference is power factor. If I had unity power factor, my motor would never start and turn. The question is, where are you getting your power factor from? Where are you getting your VARs from? Where are you getting that reactive energy from? Everybody uses this analogy, and I think I know why. You know, if you see an engineer or electrician or anybody who deals with electricity in a bar drinking beer, they are doing research on power factor. Ask them questions about power factor and ask them. Show you what they're talking about, because that's what they're there for. We're all studying constantly. And that's why we use this analogy. If you think about a glass of beer, watts, the real power that is actually doing work, it's creating heat and all that other good stuff, is watts. That's the real part of the beer. That's the part that goes to the bloodstream, right? The VARs is that head on top of a beer that doesn't do anything but get into your mustache. And what do? We have to wait. We have to keep blowing on it. Let that go away, or you get it on your nose. The VARs is that foam is not doing any work. It's not going to your bloodstream. So watts and VARs together, that real beer and the foam, tells you how big of a glass that you need. And that size of the glass, that total dimension that includes the VARs and the watts, is what we call VA. All of it together. I need to have a glass large enough to handle the watts and the VARs. The size of my glass could be the size of my transformer. How do I size a transformer? In kVA. That's a lot of beer. Every time you see a big transformer, what you got to do is just look at it and say, gosh, that's a lot of beer. That's VA. So in all of this discussion of this and this boils down to a simple triangle that you probably learned about in high school. We call it the power triangle. Watts is your horizontal. VARs is your vertical axis. Your VA is the hypotenuse. All of the equations associated with this triangle, just standard geometry, apply to watts, VARs, and VA. Power factor is the cosine of theta. And what did we say before? We said that power factor is the ratio from watts to VA, right? So power factor, so cosine theta is also equal watts divided by VA. That's the cosine of theta. If you know your watts and you know your VA, what do you do to calculate theta? It's the inverse of cosine of watts over VA. And we get these from all of these standard equations that you learned back in high school. This is, what I've done here is I've thrown you a little curveball, because real is resistance. Watts is generated from resistance. I squared R. R is your resistance. Reactance is VARs. And your impedance Z, that's your VA. That theta is exactly the same as the theta with watts, VARs, and VA. It's the same angle. It's the theta, cosine of theta is the resistance over impedance. Cosine of theta is watts over VA. Depending upon what you know in your power distribution system, that's going to help you understand what the power factor is. And what this does, the other reason I put R and X in here is because your conductors, your motors, your transformers, your busway, all define the power factor of the power distribution system in its entirety. That's an important thing to understand, that every lengths of conductors make a difference. That's why Chapter 9, Table 9 has resistances and reactances, X sub L. Let's do some quick math. If I have a resistor in series with a 208 volts, my Z, remember Z is R plus JX, that's my triangle, 100 plus 0J, and 0, that J represents my reactive component, my reactive impedance. So Z is equal to R plus JX. And I could represent this as 100 at an angle of 0 is that impedance. And I want to calculate current. I have to take 208 volts, and I'm putting 208 volts at an angle of 0. If it was at an angle of 120, whatever that angle would be for that portion of the circuit, I would use it. But the important thing is that the resistance is 0 at an angle of 0. So this current of 2.08 amps at 0 at an angle of 0 is a unity power factor. Both the current and voltage are in step with each other. There's no difference. Because why? It's a resistor. It's an incandescent light bulb. The moment current starts flowing through it, you're generating heat. You are creating something when you do that. There's no delayed reaction. Now, if I add an inductor, and how do you like my my graphics design? So if I add a reactive component of 50 ohms, and that would be like an inductor in this circuit, I would draw my equation R plus JX, R being the horizontal, X being the J being the vertical axis, is 100 plus J50, and following the rules of trigonometry. R squared plus X squared, square root of that gives you the magnitude. And if I take X over R, inverse cosine, that gives me my angle. So, or inverse tangent gives me my angle of 26.56. And that's all basic math. Take a look at the previous slide. Go back in the video. I have the math, the numbers up there. So that's 118.8. And then I can calculate my current is now 1.86 at an angle of negative 26.56, and that would be called a lagging power factor of 0.89 because my angle is negative. I'm lagging. I'm at a lagging power factor of 0.89. Now, when I start applying capacitors for power factor correction, a capacitor is in parallel with that load. If that load was a motor, I would have a capacitor in parallel with the motor. If it was higher up in the power distribution, that capacitor would be in parallel with everything downstream. And we'll help you understand what that does. Motors, and you remember, and I don't know if it was where I bookmarked this, but motors, the proper switching sequence, or no, motors, grounding, marking each rating where a motor installation includes a capacitor connected on the load side. Well, it does show be based on the improved power factor of the motor. That's not the right one. So remember, there was a discussion of full load power factor. Motor power factor will be different based upon the range in horsepower and what percentage of the load. Look at, this is a 3 to 30 horsepower motor, and this is a 40 to 100 horsepower motor. At a half load, you're at 70% instead of 70%. At 3/4 load, you're at 79%. At full load, you're at 83.9% power factor. So your power factor got better the more you loaded it up. So the more closer you got to full load amps. So that just helps you. Using motors efficiently is also applies with using motors at or near their full load amps. Now, I want to give you understanding from a triangle perspective what this means. So if I look at this, if I had 100 watts and 100 kilovars, my hypotenuse is 142. If I take 100 squared Let's just do the math. 100 squared. 100 squared. Geez, oh man, I can't see. So 100 squared, and then 100 squared, add those together, take the square root, 141.42. So that's, I put 142. Whoopee ding ding. All right, so if I want to know the angle, if I want to know the power factor, I take 100 over 142, and I get 70%. What's another way I can get to power factor? I could also say theta is equal to the inverse tangent of 100 over 100, and that's 45 degrees. That's theta. But what is power factor? Power factor is cosine of theta. Cosine of 45 is 0.707, 70% power factor, or 71% if you want to round up. Right? So there are multiple ways to get what your power factor is, and it's based on the triangle. That's the beauty, what I really love this whole discussion. Now, let's say that I correct my power factor, and now I only have 33 VARs. My watts stayed the same, but I'm a third of what I was with regard to VARs, okay, reactive component. Look what my VA did. My kVA went down to 105 from 142. Lowering the amount of VARs that my system needs decreases the kVA. And what does that tell you? That if I correct my VARs downstream, I can reduce the size of my upstream equipment. Could be a transformer. I can reduce the size of the transformer. So correcting from 70% to 95%, I went from 142 kVA to 105 kVA. How did I do that? If I add capacitance into my system, I can let the VARs come from the capacitors, not from the utility. So my overall kVA can come down from 142 to 105 when my capacitors are providing this 67 kilovars. So I would have to size a capacitor bank to give me 67 kilovars based upon the voltage I'm applying it at and the frequency that I'm applying at. The reactance is 1 over j omega c, and omega is 2 pi f. So 2 pi, we know those numbers. F is 60 hertz. If I'm in another country, it could be 50 hertz. And C is my farads. In many cases, you're talking microfarads, and you have to take remember, micro is 1,000,000, so you have to divide that number by 1,000,000 if you want microfarads. So now, how would I apply this in this application where I have a transformer and I'm feeding a motor load? I bring in if my total VA with that motor being, say the motor is a 0.7 power factor, or whatever it is, 0.85 power factor. My VA is based upon the power factor of that motor, plus remember the real and reactive components of the conductors that are feeding it. I got to consider everything. If I add a capacitor bank to provide the VARs to the motor, I reduce the overall VA that the transformer is seeing. That tells me I can reduce the size of my transformer. So my original VA, which was a larger number, is now a smaller number that the transformer is seeing because the VARs are being supplied by what? The capacitor bank that I'm putting in parallel with that motor. And this is a very typical application. This is why you see in 460, it says where a motor installation includes a capacitor connected to the load side of the motor overload device. Replace that transformer with a motor overload device. It's going to see less current than what that branch circuit sees going to the motor. Why? Because the capacitors are providing the VARs. So it reduces the VA that the transformer is seeing. If that was your motor overload, it would be seeing less current. And if you size it for the whole current, and it's not getting there, then you're not properly protecting the motor. So the rating or setting of the motor overload device shall be based on the improved power factor of the motor circuit. So That's what they're talking about. That capacitor, and maybe in one of these sessions, we will do a capacitor calculation to show you how we calculate that capacitor, and I'll show you what the circuit looks like. That transformer, without a power factor correction capacitor, has to be sized for the entire glass, which includes the foam and the beer. If I put the capacitor down at that motor, on that same bus as that motor, downstream of the transformer, my transformer has to only be sized for the beer, because I've removed the head and I've supplied it to the motor from a separate source downstream. It sounds funky, it sounds weird, but that is exactly what's going on. I don't need as big of a glass to hold that beer, because why? I scraped that foam off and I supplied the foam somewhere else. That capacitor bank is providing the VARs for that motor to do its job. The motor still is using, its power factor is still 0.85. You can't change that, because if it wasn't 0.85, it wouldn't turn. It's still 0.85. Now, what you have to do in a power distribution system, the designer has to say, where do I put power factor correction? Maybe you put it up at the service entrance. And why would you do that? You want to reduce the cost of your bill from the utility, because just maybe the utility is giving you a power factor correction penalty. And if you improve your power factor, which means you're not pulling a total VA from the utility, they can provide you a lower amount of VA. You're a lower footprint, you're a smaller footprint on their system, because you are providing the reactive component to VA, the VARs, locally. You're a generator. You're a utility. You can look at that capacitor as a utility, a little utility. And if you put it way up there, it's probably a big utility. Maybe you put it down here on the secondary of this transformer. And maybe you add this after the fact. You don't have to just think about it from a new design. You can add a capacitor bank because you're adding loads and get more capacity out of this transformer. You're not getting more capacity out of the transformer. You're basically helping that transformer by providing the VARs so it doesn't need as much VA. So you can add a capacitor to increase the capacity of an existing power distribution system if you're running a poor power factor. You don't want to correct it to unity. You want to bring it up maybe to 0.95, 0.96, something close to unity. And you can add enough capacitance to add those VARs and reduce that VA for that transformer and get more capacity for your power distribution system, so you may not need to buy another transformer. You can do that at the motor. And that, what is that? It reduces voltage drops. So you might add a capacitor. If you have a feeder or a branch circuit going out to a motor circuit that is long, you can reduce the VA, reduce the amount of current flowing in that feeder, reducing the voltage drop, because you're providing the VARs closer to the motor. You see where this is going? I can reduce my bill. I can increase the capacity of my system. I can reduce my voltage drop. Why? Because I'm providing the VARs locally. So kilowatt loss reduction, I can have some real savings, but often it's overstated. And here's what we're seeing in the industry, especially in residential. They sell these little gray boxes, and they'll say, we're going to put this on your house. And they'll get the homeowner over and they'll say, look, they'll put an ammeter on, and they show the ammeter, and they'll show, I don't know, say 80 amps. And then they turn their little gray box off and it goes down to 70 amps. They say, look, we're saving you money. But they're not. Why? Because they're showing you the reactive component. They're showing you the total VA. And the VA may have gone down. But remember that slide. What do you get billed on in a residential unit, right? What do you get billed on? Watts. You don't have a power factor. You don't have a power factor penalty in a residential home. So in both of these cases, my VA moved from 142 to 105, but look where my watts stayed at 100 watts, kilowatts. And if that's all I'm getting billed on, power factor correction does not help your utility bill 1 cent. In a residential home, power factor correction is not going to help your utility bill in 1 cent. So those little magic gray boxes that they put on the walls of residential homes, and they'll show you, look, we're going to measure overall current, and that is your kVA that they're measuring. And they'll show you that the kVA goes from 142 down to 105, and they'll say, we're saving you money. And you may say, wow, that's incredible. I want to buy one of them. Oh, no, you can't buy it, sir. Well, you have to have a $29.95 a month. Your return on investment is out there. Come on. It's not magic. So sell unknown residential and commercial customers little or no knowledge, the kilowatt versus kVA look, and that's what they're doing. Now, across the state, these penalties that are applied from utilities, we can see those for heavy industrials. We do see those across the country, but not every part of the United States has a penalty. Just keep that in mind. Talk to your utility. So the primary benefit, reduce your electric utility bill, and the payback can be less than 2 years, depending upon your usage, depending upon your penalties and your current power factor and what you're correcting it to. You can increase the system capacity, improve voltage regulation, reduce losses in transformers and cables, and it may reduce harmonics in the power system as long as you're applying the filters. Again, that's another important thing. You've got to think about series resonance and harmonic. The moment you start putting capacitance intentionally in the system, you've got to think about making sure you're doing it correctly. This is just an example of a bill, how they're getting your total kilowatt hours, and there's your kilovar charge. Right down here is your kilovar charges. So there's your 263,000, and there's your power factor and your on peak, etc. So you have to look at your bill to see if you indeed are do have a penalty. Now, loads with low power factor, air handling, HVAC, pumps, elevators. Again, this, keep in mind, variable frequency drives might present a different footprint for you. Be mindful of that. Elevators, compressors, computers, process machinery, and I would say LED lighting and inflorescent lighting. And I think I have some numbers here. Here, this is from any-lamp.com. The power factor of a light source indicates how much blind current is generated. The power factor is calculated by dividing the apparent power with the actual power. The power factor of an incandescent light bulb is unity, right? And that's, if you look at 220, it says unity power factor. The apparent power and actual power are even, but the power factor of an LED can be 0.3. That's big. 0.3, as low as 0.3. I've looked at different manufacturers of LEDs, and remember, if your power factor, for example, if they said that your watts was 5 watts, or say it's a 100-watt light bulb, and say it's 100 watts of LED lights, at 0.5 power factor, it would be 200 VA. Think about that. It's twice. 0.3 is even worse. All right. How about fluorescence? Lux. This is blog.1000bulbs.com. And there was a study that was done, and I think I have some shots from that study. Lux Review gave a great example of the differences between the power factor ratings of two 20-watt LED floodlights. The first LED floodlight has a power factor of 0.95, while the other has a power factor of 0.55. The LED with a power factor of 0.95 would draw 0.092 amps, while the LED with a power factor of 0.55 would draw 0.16 amps. That's a lot more current. Why? Because it's the same story of VA. Now, if you put power factor correction in, different story. I'm bringing it back closer to unity. But the poor power factor results in higher currents, results in larger VA, more capacity that you need. Now, this is compact fluorescent lighting systems. 13-watt quad tube compact fluorescent with magnetic ballast, 0.54 power factor, 0.5 power factor. There's a 16-watt quad tube quad tube compact fluorescent lamp with HPF electronic ballast, 0.91. So the ballasts make a difference. The type of the light makes a difference. You know what that tells you? Go talk to the manufacturer. And be careful. Remember, when you talk to someone who's very familiar with ASHRAE, they always talk about watts per square foot. Why? Because about 100 years ago, a watt, there was no power factor. You didn't have VA for lighting loads. Why? Because it was all incandescent bulbs. That is not true today. Today, we are driving more LEDs, compact fluorescents. They are not unity power factor. You may need more VA capacity to supply an LED or a compact fluorescent solution as opposed to an incandescent solution. Why? Because of power factor. Yes, can you get the 0.99? Yes, you can. 0.98? Yes, you can. Are you going to pay for it? Yes, you will. So you got to understand what you're buying, what you're applying, and what you're installing, and how to do the load calculation. Because remember what it said in 220. 220 tells us, and you probably remember the section better than I do. 220 tells us in 220.18, maximum loads for circuits supplying lighting units that have ballasts, transformers, auto transformers, or LED drivers. Okay, the calculated load shall be based on the total ampere ratings of such units and not on the total watts of the lamp. This is why. Because of power factor. VARs. The VARs will get you every time. And you can't read this, but you will be able to in a second. These are typical uncorrected power factors in facilities. Breweries, 76.80% power factor. Cement factories, 80 to 85. Chemical, 65 to 75. Coal mines, 65 to 80. Look at these numbers, 75 to 80. Foundries, forge, hospitals, 75 to 80. Machine manufacturing, 60 to 65. I don't know what year this was put together, but I'll tell you, I'm sure with LED lighting and whatnot, depending upon what lighting you bought, if you bought all LED lights and they're all 0.3, these numbers are going to be blown through the floor. So you got to think about the power factor. We already talked about that. Typical charges, we already talked about that. Okay, so, and I think, yep. That's all I have to say about that. I hope that I gave you a little bit of a flavor for what power factor is. The imaginary world is VARs. Motors need it. That driver in that LED light needs it. You're not going to get rid of it. You can supply it from another source somewhere downstream and alleviate the footprint of your power distribution system. I'd love to sell you huge transformers. I'm sure manufacturers out there would love to sell you big conductors, big breakers, big fuses. But if you apply power factor correction correctly, you can reduce the footprint of your power distribution system as long as you have a power factor issue. And I'm telling you, if you're using a lot of LED lights and you may have gotten the lowest bidder, you might be using a lot of fluorescents. You might have a lot of motors. You might be a very prime candidate to increase the capacity of your system. Forget about the bills. Increase the capacity of your system without changing a thing. And follow the National Electrical Code and how you do your load calculations, how you do your sizing of your conductors and protection of the capacitors. And I'm telling you, you are in Fat City. All right, I've gone well over my my limit, and I appreciate your time, and I appreciate your focus on safety. Thank you for your emails and your comments and suggestions. Please keep those coming. If you have an issue with anything you hear on my program, question it. If I say something wrong, put me on the table and I will own up. I got thick skin. So it's all about doing the right thing. It's all about electrical safety. It's all about saving lives. So there's no pride in that, in being wrong and hiding it. So if you hear something come out of my mouth that you question, please send me a note and we will address it. We'll keep it real. All right. Thank you for what you do for the electrical industry. Thank you for what you do for electrical safety. And remember, please, I will see you next week. I think, yes, we'll see you next Tuesday, and it might be a recorded session again as well. I'm not sure, but we'll see. Hopefully, we will be live. And we will see you soon. So thanks for what you do for the electrical industry, for electrical safety, and for for everything. So take care, stay safe, God bless, and please, whatever, by all means, stay healthy.